Hey everybody, this is Bruce and the dog on the floor, and today we're going to be talking about FluxML, a Julia machine learning library. Actually, it's an umbrella of libraries that it's going to use to actually make improvements to a model over time, and the improvements that we're going to talk about are going to use something called AutoGrad or Auto Diff, which means we're creating differential equations that detect the rate of change for a function, whether it has 1 dimension or 10 dimensions. And we're going to actually do some of the work ourselves so that you can see exactly how the Flux library works. So it's going to be pretty exciting. So let's get busy. You might be surprised to see me working from the console this time, but the reason is that I need to control exactly when various commands get executed, and sometimes the Pluto notebook propagates changes from one cell to the next. I don't want that to happen, so we're going to stay with the plain old console. So we're going to be using Flux, and we're going to actually use Flux and its gradient system, and that means we're going to be making the updates to the model ourselves rather than having the optimizers make those updates for us. And that means we're also going to need the API flux.optimize update. We're actually going to need this, and that exclamation point means that there are side effects. So the side effect in this case is that we're going to update the arguments in our model, right? Or the parameters, that weight and the bias, so that we can make better and better predictions. But we're also going to need a loss function, and to make that prettier to consume, we're going to just do using on Flux losses.mse. And remember, this is the mean squared error. So we take the sum of the squares of each observation, compare the predicted against the actual, and then so square that value and then take the average of those. And that gives us a pretty good indication of loss for many machine learning problems. So that's what we're going to do. And we're going to be predicting a function, and the function that we're going to predict is 4x plus 2, right? So I picked this function because it has a weight and it has a bias, and we're going to actually pick the parameters of a model that makes predictions, and we want to be able to check the impact of each one. So what we're going to do is our predictor is going to be a single dense layer with one input and one output, right? So now we have this dense layer, and we can take it and we can get the parameters of it. So the P's is equal to params predict, right? And so we could see that the prediction, if this was a perfect prediction, this number would be 4, and this number would be 2, 4x plus 2. So as we peek in on the optimizer's progress, that's what we're going to check. Okay, so you know that in order to make predictions, we need to have our knobs and levers, and we have them. We need data, and so let's go ahead and build that data now. So we need x's, and our x's are going to be the range of numbers from 0 to 5, and just so we have something that works with our model, we're going to horizontally concatenate those. And what this would do is give us a matrix with only one row, the range from 0 to 5, right? And so what I want to do is take apart this thing and make something that looks more like hcat and the list of 0, 1, 2, 3, 4, 5. So that's what this ... does. It means instead of passing a single list, we're going to break apart that list into individual arguments like that. Okay, So now we have X observations, and remember in Flux, the models represent these observations as columns, and the features are represented as rows. Here, there's just one feature, and that's the number X, and based on the X, we're going to make a prediction, and let's call the prediction actual. And then all we're going to do is call our function in broadcast mode. We're going to broadcast that to every element of X. And so we should get a horizontal row, or a row where every column is one of our observations. And that's what we get. So 0 times 4 plus 2, 1 times 4 plus 2, 2 times 4 plus 2, and so on, all the way across. So now we have our data, and we have a model, so we can make a prediction right now. So we can say predict X, and that's a pretty terrible prediction, right? Because we've seen what the parameters look like, and we need to make these better over time. But the way that we're going to do that is with a model, right? And so we have that model, and we're going to actually build a loss function to objectively measure how good or bad a prediction is. And our loss function is going to take in X's and then actual predictions. And we're actually going to base that on Flux's MSE, or mean squared error, where I'm actually going to predict values based on X. And what does that look like? Well, we did a predictive X right here. Right, so that's going to take these and say, okay, how bad is that prediction? Compare those to the actuals. Right, and so the actual is this data right here. So that's the broadcast data. So now we have a loss function, and we can actually take gradients. So part of Flux is this gradient function. And so we can actually take gradients. So I'm going to say my grads equals, and they're going to take the gradients of some function with respect to inputs, right? And so the inputs are the parameters that I picked up, and the parameters are these. And so the inputs, or the function that we're going to give it, is the gradient function, right? So take no arguments, but then build us the function. So I want to call the loss function, and the loss, I want to run this one right here, right? So I want to basically call the loss of the X's, and then I want to pass the actuals, right? Because I'm going to run the predictions on those X values, and then I'm going to compare it against the actuals. And if you look at this set right here, this is one set of training data, the observations and the actual values for the training data. And remember, these are going to be real world observations based on inputs that we typically are learning based on, right? Okay. Gradient's not defined. That's because the function name is gradient. And what this is going to give us is a series of gradients at the respective positions that we asked for. And so those positions are the parameters in our list, right? And so we have, so actuals not defined. That's because it's actual singular. Okay, let's try this again. So there's a little bit of a compilation step that happens the first time, and then after that, it's going to be fast. So now we have parameters, we have gradients, and I can say, so let's see what those parameters are. So the parameters, so the first one, so this is the same as the predict.w, right? And the p's of 2, that's a 0, and that's the same as the predict function, or the predict model at b. Okay, so now we actually have gradients. So I can take the grads at 0.0. Let's see. Grab the gradients. Only references can be, oh, I see. So it's saying I typed 0.0 and what I need to be giving this is a parameter reference. So I need to use the P's sub 2, right? Because that's my bias. Okay, and so this says, hey, you are we're too low, so we're actually going to make this greater. And let's say what it says about the gradient at the first parameter, and says that's too low also. We need to be kicking that up as well. So let's go ahead and do that. Let's actually apply some updates. So I want to first update, and I'm going to give it the parameter we want to update. And then the new value, right? And so the parameter that we want to update is P1. And what's the new value? Well, it turns out we need to know a learning rate. So let's specify a learning rate. Let's say it's going to be 0.1, right? Okay, so this learning rate, now we can say the new value. And now I can say update, and I'm going to say update P2 or P1. And I'm going to say take P1. I'm going to update this with the grad or the gradient at P1, right? And I'm going to multiply that thing by the learning rate. Right? So this gives me the proportion for each of the arguments, right? So if you think about directions on a map, if I'm going somewhere towards the southeast, then I need to know how far south and how far east that I'm going. So the gradients give me the precise proportions, and the learning rate defines how big the step I'm going to take might be. Okay, so now I've got this. You know, before we do that, so I'm going to take this and I'm going to save it. But let's go ahead and get the loss. So the loss of x with respect to the actual. Okay, so my loss is 89. And so that's as bad as it'll get if we're doing this well. And so now I'm going to say update the first parameter, and remember this is the weight with respect to the gradient and the learning rate. P is not defined, so actually that's because it is the parameters, the P's. Okay, update. So I've left off the exclamation point. Now we're talking. Okay. So what we've done is we've updated the first parameter to make it slightly better. And we've also updated the, we need to update the second parameter, right? So, and this is the proportion times the size of the step that I'm taking. Okay, so now if I get the loss, so now let's see if the parameters are different. Okay, so the parameters are a little bit different. We could see that it closed the bias pretty well, right? And the weight, let's see if it improved that as well. So let's see, so the loss of x with respect to the actual numbers. Okay, so our loss went from 89 to 85, so it went down. And so we're going to do this over and over. So let's go ahead and do this much again. So I'm going to grab more gradients. Right? And so this time we're going to take the, this time the loss is going to be different, right? Because we are within the loss, we have a prediction based on our model, right? Okay, so there's our gradients, And now we can go ahead and say, update the second parameter. This time, let's say 4p in p's. Let's say update. And this time, let's update p, and then grads at p times the learning rate. Let's let that fly, and then let's get a loss update. Loss of x with respect to actual. And this has gone down again, but it turns out that we're going to have to do this a number of times. So let's say for e in epochs, and let's say the epochs is 1 to 100, right? And then let's do all of these commands, right? So let's run this. So these are our gradients, right? And remember the gradients, this is just the slope of the line that determines how bad we're getting, how fast. And we're going to do an update based on these gradients in the optimizer, right? And so now I can run this command. Let's tighten this up a little. And let's say we could do a print line of loss of x with respect to actual. Okay, and let's see what happened with our losses. Yeah, our losses started pretty high, and they started diving down and down and down. And now we can see the parameters. So the parameters, this is supposed to be going to 4, and this is supposed to be going to 2. So we are pretty close. This is learning exactly the way that we expect it to. And if we actually run our training loop again, we can expect this to get even better, right? And here are parameters. Now we're getting closer to 4, and we're getting closer to 2. So how close should you get? How many iterations should you run? Well, this is where the art and the science of machine learning kind of blurs a little bit. There are some simple models where we can automatically detect some type of convergence, but normally it's going to take some tuning of our methods and algorithms and the individual types of optimizers that we decide to use. But what we've shown you, this is the gradient descent optimizer. So we could do a very similar step by using the gradient descent optimizer and the train function that's built into that to actually update the parameters for your model. So I could do this automatically based on any number of instructions. So as many as there are optimizers supported by Flux. So how does this all work? Well, did you catch the shift in landscape? Rather than catching the gradient for the individual function that I'm trying to model, that's the f function, right? So f of 1 is 6, f of 2. So there's a gradient for that function, and that gradient is really going to be 4, right? That helps a little bit, but it doesn't really help us that much in terms of a more complex formula. So what we actually did, we didn't catch the gradient of that mx plus b or the wx plus b formula. What we did was we picked up the gradients for this function, right? This is the loss. Because as the gradient for the loss is steeper, that means, hey, this is getting worse and worse quickly. And as the gradient is getting more shallow, this says, hey, this is not getting bad as fast, right? So what we're going to do is we're going to chase the gradient in the negative direction, right? So if it's getting bad quickly, we're going to flip that gradient on its head, and we're going to apply the changes in the model completely based on the gradient. And so what we've done is we've shifted the landscape, and we've shifted it from rather than the function that we're trying to model to the loss of the function that we're trying to model. And that actually has some great properties in terms of actual, not just machine learning, but also statistics and numerical computing in general. This right here, this function, is really the secret sauce in Flux and a whole wave of new machine learning frameworks. It's really the core thing that you need to understand. How bad are things getting worse? Because if we know how quickly things are getting worse, we can flip that gradient on its head and make it better that quickly as well. And that's really an excellent thing. From Bruce and the dog on the floor, this is Groxio Learning.